Find the answers to questions you may or may not have asked yourself here at Science, Conversations on Cognitive Science, hosted by Elisa Percolla and Sönke Löw. Today we are going to talk about one topic I honestly don't know that much about, which is Parkinson's disease. We have a guest who has written her master's thesis on this disease and has researched the neurocorrelates on it. And I honestly can't really say a lot about a personal relation to it because I don't know anyone who has it, or I just know some, things I've heard in lectures or read or, just stumbled upon, but never really gotten into it. So I'm really excited to talk to our guest today, who is Elisa Percolla. And, we are going to learn, I think, a lot in today's episode. So welcome.
Thank you for the invitation.
And now, as always, we like to play our little welcome game where where I start sentences and we want you to spontaneously continue them.
Okay.
And the first question would be, as a kid, I always wanted to be.
A collectionist or a lawyer.
Okay.
A collectionist, what for?
So basically, as a child, I was extremely introverted, but with quite some loud ideas. So what gave me joy was to collect pencils. Because first of all, they were really cheap, which was assuring me that I could get a new item every week, right? There was some, certainty about that. And I had these white mugs on my desk, and at the end I had 300 or something like that. And I was also collecting aquaria with this keychain, and I loved to have them hanging on my wall. And they were playing with the morning light and creating this representation on the wall. And it was really, it gave me a sense of peace and quiet. And that's why I will always like to collect beautiful things and take care of them. But the loud part was related to the fact that I also used to be a writer. I started to write poems when I was 10 years old. That's a little bit early, but yeah. I actually published the first one when I was 11. And that was my kind of secret warrior side, so to say. And they were about freedom and about human rights. So sometimes I was putting this white shirt on that I used to have, and I was playing the lawyer with my mother that was like sitting on the couch and listening to me. She used to say, "Oh my God, you have very strong topics. I'm not sure I'm ready to see you as an adult." And she's still not sure she can handle it, but we can try. So yeah.
Nice. Okay, the next question is, if I was an emoji, I would be.
Oh God, a slice of pizza.
Okay.
It depends on the moment. Maybe a red balloon, a sunflower, a crying emoji. I'm not sure.
So you would be a whole emoji collection.
Maybe. You need to give me like a few of them because it really depends on the moment.
Yeah, but I think I can really relate to like the red balloon thing. Because it's also a lot used, but I've never even considered someone answering that ever. But yeah. It's nice that you did. The third sentence would be, my favorite thing to do on a day off is?
I love the nature, so I would love to go to the forest and pick mushrooms. The legal one, okay? The one that we can cook and safely eat with some friends. Just grab a cappuccino in the city in this very old-fashioned cafes, basically, and read my book. Do some yoga, really standard, quiet stuff, I will say. But I also I need something that is literature related or visual art related, and something that allows me to express myself. That's my concept of a good, nice, non-working day.
Do you still write your poems?
I do, but the style is slightly different. So when I was a kid, I was obsessed with rhymes. Everything was rhyming, and I was also writing poems for my best friends. And to be honest, I received one a few days ago, and oh my God, it was so kitsch and cute at the very same time. Now I feel like it's more like Thomas Stern Eliot, I will say. So it's a stream of consciousness, is similar to similar. I mean, it's inspired to James Joyce, so I feel like I combine journaling and writing poems all together. So it's a form of liberation for me and the form of expression as well. So they got a little bit more complex when it comes to the vocabulary that I'm using, and I left rhymes behind. So the structure is less, the melody doesn't sound like a song any longer. Yeah.
Do you write them in English or?
It depends on the moment. Sometimes I write them in Italian, sometimes in English, and I also wrote one in German. And
Nice.
I tried something in French when I was studying French at school.
That's impressive.
It's just because you haven't seen them. They are very, very basic, but I feel like it depends on the emotion involved. So, of course, Italian is my mother tongue. I feel like the complexity that I can express when I'm using my mother tongue will always be something that I cannot get with other languages. But I moved to Germany 5 years ago, and I've been using mainly English because there were a lot of challenges for me, new things to learn. It was a little bit of a cultural shock, okay? I won't deny that. And I wasn't ready to feel so fragile and use German all the time. I was feeling really embarrassing because of my accent, so I decided to stick to English. And I developed a new Elisa, basically, which means that now, yes, Italian is the most emotionally bounded language in my brain, but I also evolved in English, so to say. So there is some sort of English Elisa that sometimes want to write their own poem, and yeah.
Interesting. Yeah.
It's like in the film Split, when there are, different personalities, but I hope I'm still, keeping all of them together in one healthy subject.
But I've heard that quite often, that people who speak multiple languages feel like slightly different people in different languages, so it does make sense.
The next sentence is, right now I'm most fascinated by.
Mental health discoveries in my research field.
Okay, yeah, we will talk about that in a bit. And the last question is, I know it's time to call it a day when.
I cannot drink another coffee because I won't sleep. So if I can still drink coffee, so it is like still coffee time, then I know that I can get some energies out and do something new. But if I feel tired and it's too late for another coffee, maybe sleep time. So I should start switching on my lavender candles and do my beauty care rituals.
What time is it for you? So what time would be the last time for you to have a coffee?
I try. This is, part of my new ideas for 2024, to have my last coffee not later than 2 right now. Mm-hmm. And normally the effect stays with me because I am normally quite passionate and enthusiastic about what I'm doing, till 22, I will say, and then I slowly start to my daily decay, so to say. But when there is something interesting, I feel like I get this extra kick of energy, I would say. But that's the moment around like 10-ish, so that I'm like, okay, let me switch off, probably.
Yeah.
And now we come to your scientific background. If I understood correctly, you only did your master's here in Osnabrück, but did your bachelor's somewhere else. So how did you discover cognitive science, and how did you discover your institute? Maybe you can shortly tell us how you got here.
That's an interesting story, actually, I hope. So for my bachelor's degree, I studied in my hometown. So I am Sicilian and I'm coming from Catania. Sicily is an island in the south of Italy. And I was studying communication and linguistics, basically. I did a lot of sociology, of cultural processes. So, for example, my bachelor's thesis was about Charlie Hebdo and the killings of January 2015. And I was really interested in that kind of mixture between science and real life, so to say. And then I started to work at the same time while I was still a student for a professor, which was the head of the neurocognitive department of the University of Catania. Her name is Renata Gambino. And we were mainly organizing conferences and events and seminars with professors coming all around the world, which were somehow connected to the cognitive reception of cultural content. So eye tracking related to book reading in the evening or theater performances and so on. And I was madly in love with what I was doing and reading the papers to prepare myself for the conferences. And sometimes I had a few questions for the professors there. That's also how I met, for example, Professor Semiyazaki, which is the head of what nowadays we will call neuroaesthetics. And I also met a few professors, actually, that were teaching at the University of Osnabrück. So Professor Alexander Bergs and Mark Tanner. So one day I just opened the door of the office and Renata, so Professor Gambino, I used to call her Renata because we have a very good relationship, was there. And she just told me, have you ever considered to study cognitive science? It was like out of the blue, out of the bluest point of the sky. And I said, not really. I don't even know, what you're talking about as a program, as a study program. I just knew the discipline. And she turned a laptop and said, hey, there's this program in Osnabrück. Why don't you apply? I actually did apply and I left the country 2 months after. So, that's how I started. It was a little bit challenging at first because of 2 aspects specifically. First of all, I will say that there's a difference in the approach toward studying when you compare Italy and Germany. And the second difference was the domain itself. I feel like humanities are more explanatory, while with neuroscience, so what I've been doing recently, you need to go straight to the point. And that's something I was really bad at the beginning. So the first time I took action and cognition, which was like my first exam, I got a 3.7. And I went there and I was like, what am I doing wrong? And the professor told me, you don't get to the point. Mm-hmm. And it was difficult for me to understand that it was really true, but it was how I used to approach problems related, I don't know, to religion, to the perception of modern satire. You don't have data, so you have to navigate around the problem, so to say. And so I studied a lot of neurobiology and neuroanatomy to get the foundations of what I wanted to learn. And then I feel like I've been quite patient with myself, or at least I tried. And what I haven't done maybe in the best way, and I will use as a suggestion for future CACSI, is to try to put our beautiful research domain into the right perspective. And what I mean is that I always had the feeling that I didn't know enough. And quite a lot hyper-talented colleagues of mine had the same feeling. Mm-hmm. When I was done with my studies and I could have maybe a more objective look at what I had been doing as a master student here in Osnabrück, I kind of realized that the problem is that there are so many disciplines, all connected by the label cognitive science, that can be a wonderful source for brainstorming, but they can also easily create this sense of inadequacy if you misunderstand your role there and you kind of think that you're supposed to know everything. So I feel like the biggest distinction would be between AI or machine learning oriented people and more empirical or philosophical students. And I feel like I will never be incredibly good at machine learning or AI-related cognitive science because it's not even what I want to do. And now that I'm almost 30, I can say that that's okay. And so this will be my suggestion for younger Elisa and for the other younger Elisas that are starting with cognitive science right now. Whatever you decide to study, that's okay. You don't have to be proficient with psychology, philosophy, linguistics, AI. Navigate this enormous sea, but do not pretend that you can always swim. Sometimes it's okay to take a break.
And coming to your own research now, or what you've done in your master's thesis, can you put it into really simple terms as if you were explaining it to someone who has never heard of Parkinson's disease and your specific, interest in it?
My perspective, the perspective that I developed as young scientist when it comes to cognitive science, is based on the concept of embodied cognition. I do believe that everything is connected, and I think it is absolutely worth investing on that. So this is the first line, so to say. Parkinson's disease has been defined as a motor disorder for quite a lot of time. If you ask people around, they may still give you the same answer. And even scientifically, if you have a look at descriptions, so we are not just talking about conversations with our family, but really scientifically, it will be defined as a disorder of extrapyramidal neurons. What will follow is like a dopamine imbalance, which normally is mentioned quite often, and we will quite quickly move to the pars compacta of the substantia nigra.
Can you put it into more simple terms as well?
Or even...
how would you explain it to maybe a child 12, 13 years of age? Because I would assume they don't know the terms.
Okay, so we move now to children. Okay, let's imagine... Okay, now I will imagine like a fictional dialogue with the child. So probably your teacher asked you last week, or I don't know, last month, to write down an essay on your holiday trips with your family, or to do a drawing of, a beautiful landscape, whatever. I hope you are like familiar with one of these tasks, and I hope the child will agree with that. And then I will say basically what I do in my everyday life with my job is that I invite people to a specific lab, and instead of asking them to write an essay of what they've been doing or create a drawing, so a visual representation of that, I let their brain speak for themselves. Now the brain is not using the same languages that I would use with the person. So I have to find a way to translate what the brain is saying. And that's why I use a computer. And I use a methodology that is called electroencephalography, which sounds probably to a 10-year-old quite a difficult concept, but it's not, because the language that I use with the brain is electrical current, so electro. Encephalo simply means brain-related. And graphy is coming from graphos, so it's ancient Greek. I will mention Greek a few times because, I studied Greek and Latin at school, so it will stay with me forever. So grapho means to write. So we are simply writing down the trace of electric current coming from the brain. Now, once I have these writings, which will be like the same essay that you and your classmates submitted last week about your holiday, I compare them. And I can see what is similar and what is different. And when you create this comparison between healthy subjects and Parkinson patient, you can see some standard differences. And then compare different Parkinson patients as well and try to understand better how to help them based on those differences. I hope this is a little bit more simple than dopamine and frequency bands.
Yeah, definitely. You've also mentioned that the usual understanding of Parkinson's disease is more on the motor level. So motor level would mean, or what would motor level mean, for example, in Parkinson's disease?
We will talk about freezing of gait, for example, which is a very common phenomenon. So sometimes Parkinson patients cannot perform a fluent movement or cannot start a movement fluently, and that's what we call freezing of gait. Or they are slower when it comes to the performance of a movement, which is called bradykinesia. So those are the main motor symptoms. So there can be shaking and trembling. And what I'm interested in, and I feel like this is possible just because there's a general attention, on that in the research field right now, is the non-motor dimension of Parkinson. And there's so much going on under the surface. And I think that's what was really interesting for me and the reason why I decided to invest around 2 years on the investigation of Parkinson non-motor symptoms that have different categories as well.
Mm-hmm. Can you tell us what those categories are?
Mm-hmm. So basically, Parkinson himself, which was the person who wrote the essay on Parkinson, on a shaky palsy, in 1817, declared that, for example, senses and intellect are not injured in Parkinson. This was the first official claim, which was already disclaimed a few decades ago, and that's what we are working on. So, for example, olfaction can be quite commonly impacted in Parkinson.
Mm-hmm.
The range of severity changes a lot, so they can have just impaired olfaction, or sometimes it can be almost impossible for them to recognize odors properly.
What does impaired olfaction mean in general? So do they just not smell? Can they not differentiate different smells, or is it all of it?
It really depends on the clinical profile of the patient. So some of them, they have like normal functions. So there are like no problems related to the quantitative or qualitative assessment of odors. For others, it's reduced. For others, it's significantly reduced. And then there are some patients that struggle maybe with specific smells.
Okay. Yeah.
So, and the reason for that is that actually, one common background theory on Parkinson is Brack's 6-stage hypothesis. And he mentioned basically that probably Parkinson may be interpreted as an immune response to a neurotoxin that is coming from the outside world. The reason why olfaction is the sense impacted is that this toxin will find its entrance through the body from the nose.
Okay, yeah.
And that's also why the symptoms may be so different, because the impact of the toxin with the nose, of course, depends on so many environmental factors that, make it different to quantify what is going on. Then, following the trajectory, actually, that Brack described, we have gut disorders. Then there are like disorders related to the circadian rhythm. So a lot of people think that Parkinson patients do not sleep well because they have Parkinson. So it's a second-order effect. Mm-hmm. But actually, sleep disturbances are already part of the spectrum of Parkinson.
And do they just not sleep well? Do they wake up a lot? How far do they sleep different from a non-Parkinson patient?
Restless leg syndrome is more common, and then the quality of the sleep itself is impacted, so they do not get enough restorative sleep, so to say. They have recurrent awakenings during the night. So yeah, again, it depends on the profile, I will say. Mm-hmm. So if you had the chance to have a look at an fMRI, for example, of a patient with Parkinson. So an fMRI is, let's say, the photos of the brain, because let's try again to keep it as simple as possible. EEG will be a song, because we are having a look at the temporal dimension, so we focus on the duration of like something, while fMRI will more be like a video of it, like a photo. And we can certainly say that the dysfunctions that we are like discussing right now correlate with certain lesions in the brain. So depending on the lesion, you will find certain dysfunction to be more or less prominent.
So on the cognitive level, we had olfactory impairment, sleep impairment.
There are also psychiatric features as well. For example, so depression is one of them, and apathy is another one. And it's super interesting to try to disambiguate clinical depression from depression as a key feature of Parkinson. And sometimes, of course, they mix, mm-hmm. because the disease itself then can elicit quite heavy causes to our mental health.
Yeah.
And then what I'm doing, so now we go to what I've been doing, is that another domain of non-motor symptoms are mild cognitive impairment. And there we have, for example, problems related to memory, learning, visual recognition, and attention.
Are there any, I'm going back to some basics maybe. Are there any risk factors? Like, is it clear that, like, is Parkinson's disease something that runs in a family, or do we know anything about that? How we can, like, assess the risk of a individual person to get Parkinson's disease?
I will try to answer this question because it's a super complex one, and I think I'm not like hyper qualified for that, but I will still try to tell you what I think. Of course, if Parkinson is already in your heritage, there's a correlation with that, which is normally stronger, for example, for Alzheimer. So when in general we have a look at pathological populations and neurodegenerative disorders, there is a genetic correlation, no doubt about it. Then there are also other factors actually that can play a role. So I feel like there was, for example, a case study related to Italy. That's why I remember that. And it was about, I think, some young people that were trying to create some drugs at home, actually. And they used the wrong components, and the toxin actually caused them some Parkinsonian symptoms. So I feel like we need always to understand, first of all, what we are talking about, because we can have Parkinsonism or Parkinson disease. And when just the motor symptoms are prominent, we will talk about Parkinsonism, so this kind of motor features, and where the entire spectrum is there, we will talk about Parkinson disease. And maybe certain regions of the world have an incidence which is higher, but is a quite complex, I think, environment to explain and to navigate. What I can tell you is that what I find fascinating is that with EEG, I could detect some traces of possible Parkinson evolution from your brain before the onset of motor symptoms.
So you can kind of, before the onset, recognize Parkinson disease in the brain.
Yeah, that's exactly what, I mean, not maybe me, but that's exactly what researchers are doing right now when it comes to Parkinson.
And where you usually find irregular patterns or, well, functionings in the brain?
So what has been used in my research field currently is an alteration of some event-related potentials. This is going to be like scientific, but let's say that they are specific signatures or biomarkers in the EEG signal. So for a person that never saw EEG, just imagine that in front of you, you have a screen full of lines, parallel lines, and every in each of this line is an electrode which is placed on your scalp. And they are somehow representing the electrical current that we were trying to describe to the 10-year-old 10 minutes ago. Now, if we put all these lines together, and we try to create a temporal dimension in which we know when a certain stimulus was presented or a certain function was elicited, like, for example, novelty detection or a specific form of learning or the recall of a memory. At some point, the brain will react to that stimulus with a function. And we can kind of measure that in terms of polarity of the wave that we see, in terms of voltage, so how strong is the wave that we're going to see in the signal, and of course, in terms of time. So, for example, when it comes to novelty detection, the first strong reaction will be around 200 milliseconds. And that's when the brain probably will start to think, hey, the stimulus that I've just seen is kind of similar to the ones that I've seen before, but it's not exactly the same. So the brain is starting to grasp that something is... And then around 300 milliseconds, so it's just 100 milliseconds more, the brain is like, you cannot trick me. This is not the same. And what is different actually is that this dot is blue and is not pink any longer. Now, what I just described, so this, of course, fictional communication between these brain waves, it's what is called in my research field event-related potential, because it's a potential, okay, so it's a response that we get just because a specific event was placed there. And as a scientist, I do that, of course, in the lab, but I mean, we do that because it is then simple to isolate the function. But we have to imagine that our brain does that every day, all day long.
Basically, whenever we see something in our environment, our brain is like, oh, something happens.
Yeah.
Now I'm reacting on it, yeah.
And they also mix together because probably in our real life there are a lot of functions that we need at the same time. Now, when it comes to Parkinson, for example, the second component that I mentioned, that is called P300, will almost always have a reduced amplitude.
So it will be weaker. So
yeah.
300 milliseconds after you saw a stimulus, your response in the brain is weaker compared to humans with non-Parkinson disease brains.
In novelty detection. So it's not just a stimulus in general, but it's an altered stimulus. In order to do that, you use some paradigms, and one of them could be the oddball paradigm. As the name suggests, you simply have a set of canonical stimuli, which may be, I don't know, pink dots if you're using visual stimuli, or you can use different types of vibration as I did for my master study.
Also tones, right? So always have the same tone and then an odd one.
Yeah, basically, if you grasp the concept, you can just play with whatever you want to play on the sensory domain and use different channels. But the point is that normally you have the 70% of the standard stimuli, and then you have the 30% of them or less. You can also slow down till the 10%, which is awkward. How do we define awkward? In order to be acceptably awkward, just one feature should be different. If it is more than one, the brain will think that is another thing. But if it is just one feature that is different, the brain will be a little bit confused for a moment and say, hey, I mean, this two looks similar, but I mean, not, identical. And that's what we will call novelty detection.
So
and N200 and P300 are the most common correlates, neural correlates to the specific function.
So, for example, when we put it back to a practical example, when you have blue dots, changing it to pink would be one component, but changing it to pink rectangle would be two components. So not, the same type of stimulus you would try to get.
Yeah, it will basically recall a different function in the brain. So something will happen, but something more difficult for a scientist to investigate. We need to keep it simple if you want to find something out. So sometimes I think from the outside world it looks like we are using boring setups. And I understand that in comparison with reality, they may look a little bit boring. And when I started, I wanted to put a mobile EEG on my backpack and measure electrical activity in the outside world. But then it's difficult to draw conclusions because there's so much going on that you cannot talk any longer about causation.
You talked a bit about, or we just talked about the visual domain, but you already said that you were working like with sensory
Tactile
input. Can you maybe explain why you did that and how what the equivalent of a blue dot is if you're in the tactile dimension?
So first of all, I did that because it is really cool. I feel like a common problem that I observe in the scientific domain right now is that we have amazing new technologies that will have an enormous potential, but sometimes the experimental designs are super old and obsolete sometimes. I would say especially in certain domains. Don't ask me which ones. I don't want to say that. But yeah, so what I did, in my point of view, was a way to bring novelty to something that was a little bit old-fashioned, because the oddball paradigm is old but gold. Okay, we are not ready to let it go. However, the old paradigm has been used with visual and auditory stimuli almost all the time for 20 years, 30 years or so. Which means that performing that in the tactile modality, first of all, is very interesting because it allows us to understand that the function itself is dissociated from the channel you use, right? It's the same. Then there are some modifications related to the tactile modality, for example. There are some early components, so let's say some reactions of the brain that we do not observe with the visual modality, but the process itself is the same. Now, if you, as Elisa mentioned, you can use a different intone if you're using the auditory modality. When you want to use touch, you have a few options. Option number 1, same body location, difference in intensity of the vibration. Option number 2, same location, difference in duration of the stimuli or frequency. Last option, which actually has been used quite often in my domain, is just target different body locations. So same vibration, for example, different body locations. And then you can measure how the topographical representation of that body location is impacting the receptivity of the signal itself.
Okay, and were you then looking like, or is that something you came up with and you had to check if that's like really an equivalent, that you can find like the same patterns, or did you just assume that and find out something new based on your data?
Actually, my supervisor wanted, Professor Peter Koenig, he wanted exactly to investigate the difference between body locations. So this was the research question that I had by default when I started my project. Then I added the, mild cognitive impairments, and I went into the difference of some neurotransmitters in Parkinson. But this was my very pragmatic starting point. So we actually implemented the field space belt. I don't know if you have ever heard of that, but it's
Could you maybe explain to our listeners especially?
So is a belt, like a very canonical belt made of a stretchable material, which does have different vibrotatile units that can be placed in cardinal directions. They can be moved depending on what we want to do with them. And it has been used originally in order to help blind subjects during navigation. And then Professor Koenig started to think, okay, let's see if maybe it can be useful for Parkinson patients as well, because they struggle with freezing of gait and sometimes they cannot walk. So maybe a certain frequency or a certain duration of vibration can help them out. And that was a project going on in 2019, actually, with a colleague of mine, which is called Elina Döring, and she's now a PhD at the Center for Neurodegenerative Disorders in Köln, I think. Now, going back to your question, what we did when we wanted to perform an oddball using tactile stimuli was to create a wristband and an ankle bracelet and not just a belt, and perform the very same vibration.
Mm-hmm.
In order to create the oddball, because it's still supposed to be an oddball, we had a difference in intensity, which means that we wanted to check how different areas reacted to the same vibration. But something else that we could have done was, for example, to invite the participants to the lab and simply send the vibration for the 70% of the experiment to the wrist, and then 30% to the ankle. So then the vibration is always exactly the same, and the difference is in the location. This will be a tactile oddball as well.
And what did you find in Parkinson's patients? So what you just mentioned, that Peter Koenig had the idea that those vibrations might also help in Parkinson's disease patients, not only in blind subjects. Why might that be? Or what was the idea behind starting this project?
The idea behind was that also in my project, we are implying that attention is impaired for Parkinson patients. So we have to take it as default knowledge based on previous literature. Walking is related to automatic attention. For us, is automatic. We don't think about that, but there's a set of movements and orders actually that are like coming from the brain and we are like performing. Now the imbalance that we notice in walking is reflected by certain frequency bands in the brain that we can analyze through EEG that are not aligning correctly. Which means that if you can find something that is training their attention, so to say, and helping them concentrating and performing a set of orders or commands, then it doesn't matter any longer what we are talking about, if it is like motor or non-motor. And in Parkinson, this is particularly salient because I've been talking about frequency bands. I don't know how clear this is, but let's say that we can subdivide EEG signal in different sub-box, or let's say lines. Imagine that as a rainbow. Okay, and every color will be like a frequency. And a frequency is simply like some boundaries that we create depending on the spectral analysis of the signal to define what is going on in the brain. So for example, we observe certain frequencies just when we are asleep. Some others are typical of wakeful life. I've been working with them because I also did some research in sleep and dreams in general. But going back to the topic, because if I start to talk about a lot of stuff, I actually get confused. It has been proved, for example, that there is a persistence of beta frequency in Parkinson. And it was already proven in 2010-2014. Now, this persistence is observable when a different type of dynamics or switch or combination of waves should be observed in healthy patients, both with motor command and non-motor commands. Which means that if the brain is reacting in the same way, maybe we can use an attentional task or a vibration that is like guiding them as a way to make even the walking path fluent. So it's an hybridation between cognitive and motor, basically. You create some sort of artificial guidance for the brain so that the gait can synchronize based on that. When it comes to that project, which wasn't my project, but that's how I understood that.
Yeah, are there any other like approaches at treating like the symptoms of it? Are there any drugs, or is that like
yeah, for sure.
And like, can you treat it or can you cure it or just treat the symptoms?
Treat for now.
Yeah.
And something that is really interesting is that the most famous component that has been used in Parkinson research as far as medicaments are concerned is levodopa or L-dopa, which will be like the grandfather of dopamine. That's how we will describe that, I will say, my research field. However, the new gossip is that levodopa is not just the grandfather of like dopamine, which, as I tried to explain before, is the main actor in Parkinson, but it's also the grandfather of noradrenaline.
So it's kind of the counter. Isn't noradrenaline the counter to dopamine in a way?
They are not exactly, fighting each other like heavily, but I mean sometimes they can have some contrast, so to say. But I mentioned noradrenaline specifically because this is something that is getting a lot of attention in Parkinson's research right now. Because the role of noradrenaline in Parkinson's disease may also explain partially the reduction in dopamine. So we always focused on the reduction of dopamine and also, to be honest, a specific type of dopamine following nigrostriatal pathways, which is like a specific, let's say, road that this type of dopamine followed to get the component of the brain that I mentioned before, so this region of the brain that, of course, is responsible for motor symptoms. And as I said, this is the stereotypical description of Parkinson. And then we have noradrenaline, which will have a different distribution in the brain, which will have correlation then with the functioning of dopamine itself, and will be maybe quite useful when it comes to the development of a possible explanation for difficulties in learning and top-down attention in Parkinson. Because then dopamine can explain part of it, but not completely. Because dopamine is more involved in what we will call sequential processing of a stimulus. So it will be the initial part of the attentive process, where what the brain is doing is putting information all together as they have the same weight and the same value. And we pile them up. Then at some point something becomes salient. And we cannot proceed like that because it will be too slow. We will have over-redundant information and we will not get what we want. So what really helped me out in understanding this process is let's imagine like a forest in front of us. And first you need a representation of the trees that you can see in front of you. Then maybe you close your eyes for a second. And if you have to recall, I don't know, a mushroom, I told you that I like to pick mushrooms, right? If you have to recall where a specific mushroom was, you need to have a look at the details of one specific tree, which means that you go back to the same landscape, to the same set of information, but you are cutting out probably, I don't know, the lateral trees because you remember somehow that it was in the middle of your receptive field, and then you go for the details. Let's say that in order to switch from this type of processing to the second type of processing that I described, we need to switch from certain areas of the brain to other areas of the brain and from certain functions to others. It's some sort of natural evolution of the process in which, in order to face a higher level of complexity, we need to let go of quantity. So do less, but do it better, basically. I don't even know if this answers your question any longer, but yeah. That's how you perform a tactile oddball, and that's how you try to read the result through EEG.
I mean, we got the idea that this research field is still very active. I mean, you are doing research in it. Are there any recent discoveries that are really, really interesting to you?
A lot of them, actually. So, can I mention two?
Yes, of course.
So, first of all, I would like to point out that the researcher that is doing the most in this domain is called Professor Solis Vivanco, and is the first one that managed actually to run experiments via EEG and prove that P300 may be a useful biomarker for Parkinson. He started in 2011 and is still conducting experiments. I feel like the last publication was in 2021. And that's beautiful because I feel like in the 80s, 90s, researchers started to say, we could use EEG for that. But proving that is a different story. So this is, first of all, let's mention him because he needs to be mentioned. There will be no master thesis, there will be no podcast today without him. Then I would like to move to Professor Sabine Krabbe, which is a professor at the Max Planck Institute in collaboration with the Center for Neurodegenerative Disorders in Köln and Bonn, actually. And what she's doing actually is that she's using animal studies in order to investigate neuropsychiatric features in Parkinson. This is unbelievably interesting, and I think that the biggest challenge is to disambiguate depression because of Parkinson, for example, and depression as a part of the spectrum of Parkinson. And the fact that she's doing that using animal studies make it like please let me know what you find out, because this is like very interesting. And but when it comes to discoveries, because you asked about discoveries, so you want some data on the table, and I will try to do that. There is a preview of an article which was out, today is the 19th, right? 19th of...
Yes.
Which was out 2 days ago. You asked me for the late ones, and I'm doing my own work. It's the latest. And it's about impairment of alpha frequencies in Parkinson. So in my master thesis, I mentioned beta frequencies and how there's too much beta there. And the reason is that beta bands, for example, correlate with consolidation of information. So the explanation behind too much beta and Parkinson would be they struggle to keep a certain set of information. And that's why novelty or updates is so difficult, because they are already spending more computational capacity on that one. The new findings are also about alpha. It's like, by the way, I mean, there was this hypothesis that even alpha was impaired. Guess what? I conducted a study on that. Welcome to 2024.
Just for people who are not into neuroscience, what are alpha waves normally connected to?
Alpha waves are connected to the very easy peasy initial processing that I described before when I was talking about the forest.
Okay. Yeah.
So if beta is consolidation, alpha is creating the reference for the consolidation.
Mm-hmm. So it's a bit the basis.
Mm-hmm, yeah.
Okay.
In novelty detection, we talk about alpha-gamma coupling. So the coupling of these two frequencies when we need to detect something new. So alpha will be the well-known book you have been reading for the last 2 years, and gamma is the other one that you want to start, but you don't start because you feel guilty about the other one on the table. And you're like, oh my God, I promised to myself I would have finished that one first. The coupling between old and new, so to say.
Okay, I think like with the time in mind, we have to come to an end here. I think we could talk about it for hours more, but...
this is the end, my only friend.
At the end of each episode, we ask our guests which fields of cognitive science are the most relevant to the topic. And I would assume that it's probably neuroscience,
Yes.
but are there other fields of cognitive science that you think that this field benefits from?
So you could definitely use AI and machine learning, or I could maybe have a brainstorming session with them and see if I can use actually their methodology in order to interpret my data. I feel like there are a lot of beautiful and amazing insights that are coming when it comes to data evaluation from that domain, and even cognitive psychology for sure. Mm-hmm. I will always try to connect all the domains ever again together for whatever topic.
I think that's the beauty in cognitive science, that you get an insight into all those different fields and then can connect them to your own topic.
Mm-hmm. And everybody can contribute somehow.
Yeah, exactly. When a person has listened to today's episode and made it to the end, what would be one thing or two things they should definitely remember and take out of our conversation?
Do not base your scientific judgment on the appearance of a disease. Dig deeper.
Thanks. That's a really beautiful closing word.
I can be so poetic sometimes.
So thank you so much for talking to us, for coming here and jumping into the scary seat of the guest.
Thank you again for the invitation.
It was really a pleasure talking to you, and well, we hope you enjoyed your first experience in being a guest to a podcast.
Yeah, I actually did.
That's so
Thank
good
you very much.
When you enjoy listening to us, the best way to support us is by following us on your chosen podcast app. This could either be Spotify, Google Podcasts, Apple Podcasts, Amazon Music, or the website of the Cognitive Science Student Journal. Another good way to support us is by following our Instagram account, which is called kaleidoscience_pod. On our Instagram account, you will also get regular information on the next episode. Thanks a lot for supporting us. This was Kaleidoscience, hosted by Elisa Palmer and Sönke Löw, Produced by Elina Ohnesorge, Elisa Palme, Sönke Löw and Sophie Kühne. Produced in collaboration with the Cognitive Science Student Journal. The music was produced by Jan-Luca Schröder. The logo was designed by Annika Richter. Thank you for listening and joining us on our journey through conversations on cognitive science.